Let's talk about these coordinate systems. So far, we've talked about everything in terms of rectangular. We may find situations that it's easier to use coordinate systems that are different. You know, if you remember polar from your Calc 2 or your pre-calc experience, that's a perfect example. So, you know, if your curve is symmetric with the origin, kind of like a circle, then something like polar becomes much easier to use. So rectangular coordinates require the horizontal and vertical distance from the origin. Polar require the distance, the direct distance from the origin and the angle between that distance and the positive x-axis. So just a reminder of what polar looks like. You know, this would be a point in x, y, but it's also a point in r comma theta. And okay, so all that's really going on here, thank you very much, is basically yeah, there it is. This is all just right angle trig. This side is x, this side is y. And that's where this relationship comes from. Just our Pythagorean relationship. And tangent is opposite over adjacent, or y over x. So this is this is basically polar. And what we need to be able to do, one of the things we're going to do today is go back and forth between the two systems. So for instance, if we want the rectangular coordinates, it's very straightforward. Basically, all we have to do is plug in r. So polar always goes r comma theta. So we would plug in 5 for r, pi over 6 for theta, into x and y. And we've got the xy coordinate. Now, where we got to start to think a little bit more is going the opposite direction. So what if we had the polar coordinates given by -4, 5? Okay. And there's just one thing I want to make sure I point out, and that's why we're going to do this one. R is easy. R is the square root of -4 squared plus 5 squared. So we've got 16 and 25, so rad 41. So there's our R. We also need the theta that goes with it. So we know that according to this, tangent theta equals y over x. So -5 over 4. Which means we've got to use the inverse trig function. So this is going to be an arctan. So, sorry for writing all over the screen here, but I want to show you something. We put in -5 force. All right. Now, something very important we need to talk about here. And this is something from your trig that I need to make sure I remind you about. Now, first off, a lot of times we'll want theta in between 0 and 2 pi. Neither of those angles are between 0 and 2 pi or 0 and 360. In fact, what quadrant do those angles lie in? The fourth quadrant. What quadrant does the point -4, 5 lie in? It lies in the second quadrant, right? So two issues with these angles. One is they're not. Let's talk radians. You know, we'll mostly use radians in here, degrees occasionally, but mostly. And unless you're told degrees, it's automatically radians. So we know that this angle here is actually in the fourth quadrant, but we should be in the second quadrant. Well, what this gives us is our reference angle. So, oops, make a little more space. So what that reference angle is the angle between the horizontal and our line. So we know that our point, let's use different colors so you guys can see this. Maybe, there we go. We know that our, we're at negative 4, 5, we're over here somewhere. Yeah. I don't. Let's try that again. There we go. We're over here somewhere. So the reference angle is the angle between our line and the horizontal. So what I know about that angle right there is that it is 0.896 plus some decimal points radians. That's still not our angle because we want to give this angle. Well, if that's 0.96, we know if we kept going, it'd be pi. So this angle is pi minus 0.896. So on and so forth. So in radians, our point would be rad 41 pi minus 0.896, yada, yada, yada. The reason I wanted to go through that with you guys is because we can't just take what inverse tangent gives us depending on what you put in. You know what, if you're in the first quadrant, it's probably not going to be a big deal. But outside of that, you got to make sure that your angle is in the same quadrant as your point. Okay. Another thing that I'll point out now, because we'll talk about it a little bit in the other coordinate systems. The other thing that you can do is if you make your radius negative, then the angle is actually 180 degrees or pi the opposite. So now we could either use the negative 0.0896, so on and so forth, or if we wanted to be between 0 and 2 pi, it'd be 2 pi minus 0.896. So because we can keep going around this circle, there's an infinite amount of ways we can define a point in polar, any single point, because we can always go another 2 pi around the circle and get back to the same point. We always keep it as simple as possible. I mean, this would be the one that we would use. We'll talk a little bit about that idea of a negative radius down the road. Questions about that? All right. So, like I said, I want to spend some time on that because I know it's something that you probably haven't seen in a while and definitely worth bringing up. All right, so these are plots that are easier to do in polar than rectangular. Now, a circle isn't too bad. This could be x squared plus y squared equals 25, but in polar, it's r equals 5. When it really gets tricky is over here on this side. If we had to integrate the area between these two, this would be a nightmare to do in rectangular because we would have to break it up into separate integrals. But in polar, all we're doing is going from r equals 4 to r equals 2, either or for this circle. But when you have like this washer, it's much easier to do in polar because the equations for it are so simple. So just a little bit of motivation for why we need polar. Not moving enough. Thank you. So what happens now is we're going to extend into 3D by just adding the z-axis. So it's polar in the xy plane. We add in the z-axis, we get what are called cylindrical coordinates. So things like a cylinder and a cone, well, hence the name cylindrical coordinates, are going to be easier to do in polar. So basically what cylindrical coordinates look like, you can see we have polar in the xy plane, but then z is just some vertical distance above. So we still have, that same thing going on in the xy. Basically the same equations as before. So it's all those polar equations, tangent of theta equals y over x. extended into 3D by just adding up a z coordinate. And that's the same z coordinate from our rectangular. So then what we want to talk about are what are called fundamental surfaces. So we want to think about, now we're thinking in 3D. If we set R to be a constant, so if we had the polar equation that R equals 2, what surface would we get in 3D? And think about what we'd get in the XY cylinder. Because we get the circle in the XY plane, then adding in the Z is going to make it go up and down. This one's kind of a tricky one the first time you see it. You know, what do we get if we set theta to be a constant? All right, so now theta is going to be our constant. So here's theta. Theta is not allowed to move. It's set as a constant. What kind of be normal or perpendicular to the XY plane? And it would go through the Z axis. Very nice. That's a tough one to imagine. This last one, what if Z is a constant? The three examples. These things are called fundamental surfaces. The reason we care about these fundamental surfaces, and we will revisit these in a couple modules, is because anytime we're dealing with surfaces that are of the shape or a combination of these shapes, we want to be in cylindrical coordinates because they're easier to plot. So if we see a cone, you know, if we see a cylinder in our figure, or we see a plane that's perpendicular to the XY plane that goes through the Z axis, we know we want to be in cylindrical. Again, kind of foreshadowing where we're going to go later this semester, so I don't want you to worry about that too much right now, but I just want you to get used to this idea. We will go through those exact 2 slides again later this semester, and I'll ask you the same questions. Spherical, last coordinate system, and then we'll start doing some stuff. Spherical is an interesting one. It depends on rho, phi, and theta. All right, so what rho is the distance from the origin, and it's just the direct distance from the origin. Notice how R had to lie in the R has to lie in the XY plane. Phi does, rho does not. So this thing that looks like a P is called rho, RHO. So that thing can go literally anywhere, and it is just the distance from the origin out to our point. Phi is the angle between rho and the positive Z axis. And then theta is the same theta from polar. That's the exact same theta we were just looking at. All these relationships, nothing you have to memorize, right? Because you'll have a note card for the exams, are all just right angle trig. All right. So the reason X is R sine phi cosine theta, well, excuse me, rho sine phi cosine theta. Well, what's rho sine phi going to give us? Rho sine phi gives us the opposite side, which is over here, and then cosine theta from before. So basically, what's happening is this part here is taking the place of R from polar. This guy here, good call. So basically, that rho sine phi is taking the place of R from our polar equations, and rho cosine phi takes the place of our Z. Again, it's just all right angle trig. Rho squared is x squared plus y squared plus z squared. That's basically from our distance formula in 3D. We're going to have all the formulas. It's just going to be a matter of knowing how to use them. And just like last time, we have our 3 fundamental surfaces we'll look at. So first off, if rho is a constant, remember rho is the distance from the origin. So if we set the distance from the origin to be a constant, what kind of surface do we get? Here, hence the name spherical coordinates. All right, theta constant, we already know that one because it's the same theta as before. It'll do that same plane that's perpendicular to the XY plane, goes through the Z axis. Now, what if phi is a constant? Let's look at phi again. Phi is this angle right here. That's a constant. And then theta is going to spin this thing around to get a cone. Yep, with its point at the origin. So those are our fundamental surfaces for spherical. And again, we will use these more later. Right now, what we're doing is just kind of looking at going back and forth. Okay. I'm going to do just a couple problems from the worksheet. I'm not going to take a lot of time on these because I do want you guys to have time to do at least a couple problems. And I've already taken longer than I meant to. I just want to do a couple of from 12.4 of converting formulas, just because it's not always obvious the first time you see it. All right, so we'll just do a couple of conversions. We won't do a lot of them. Let's talk about 3a. So 3a. We're given the polar equation r equals 5 cosine theta. This is something that can be graphed in Desmos in your graphing calculator. You just need to change your mode to polar. So if you want to convert this, at first it's hard to see how, but what we can do is multiply both sides by an r. So this becomes r squared equals 5r cosine theta. Now the transformations, the substitutions are much more obvious. R squared is equal to x squared plus y squared because we're going to rectangular. R cosine theta is x, so that equals 5x. Simplify it because right now all we know is that this is a circle. But where is the circle centered and what's its radius? Minus 5x plus something, you're close. You're very close.
Or wait, no, that's
Y squared equals 0 plus something.
That's double 5. So that's like,
Yeah, so what I like to do, I like to go to the next line, and I know that what goes right here is exactly half of this. So what goes here is negative 5/2 squared. And then we got to keep our balance. Plus y squared equals 25 over 4. Now we know we have a circle centered at 5/2 comma 0 with a radius of 5/2, because remember this is the radius squared. So, you know, I know you probably haven't had a lot of practice at completing the square. That's why we're doing this one together. You're not going to have to do we're not going to be exchanging formulas back and forth a whole lot. Again, it's just to get you familiar with these other coordinate systems. Let's see, I think I want to do just one. Oh, yeah. Let's do one more. Yeah, that'll still give us a half hour. We'll do one more and do a habit on there. We're going to do 8C. So z equals 2x squared plus y squared. And we have to convert this over to spherical. All right, now it would have been nice if it was plus 2z squared. It would have made things really easy. Unfortunately, we don't have that. So we're just going to use the transformations. So z equals rho cosine of phi. Because I don't even have these memorized. So like I said, do not try and memorize these transformations to spherical. This is a perfect thing for like the note cards. 2, and so x is rho sine phi cosine theta squared 2, and y is rho sine phi sine theta squared. So what's going to happen, you know, we're going to have 2 rho squared sine squared phi cosine squared theta plus 2 rho squared sine squared theta, excuse me, sine squared phi sine squared theta. So we've got a cosine squared sine squared, right? This is going to happen a lot. It's going to help us simplify. So we're going to pull out the 2 rho squared sine squared phi out of both of those. And we get left with a cosine squared theta. You got it, plus sine squared theta.
Which is just 1.
That's our Pythagorean identity. Now this is equal to rho cosine of phi.
So we're gonna have like. cancel.
And what we like to do is solve for rho. Okay, just like in polar, whenever we can, we like to solve for r, or in rectangular, whenever we can, we like to solve for z. Now it's not always going to be possible, but in this time it is, because what we can do is divide by 2 rho sine squared phi on both sides. And I'm only doing 1 row because they'll cancel out on this. So that gets rid of this, this, and this. That'll get rid of those. And now this is fine for a final answer, but I just want to show you where the answer on the back came from. And that is from taking this and saying, okay, well, that's 1/2 cosine phi over,
Cotan, secant, yeah. No,
yep,
just-
sine phi, and 1 over sine phi.
Okay.
And so that's where I'm going to write on this side just because I don't want to go any lower. 1/2, that's our cotangent phi. And then there's our cosecant phi. Again, this would have been fine for a final answer. Sometimes we like to write them without fractions whenever possible, hence the reciprocal